In the previous video, we learned how to construct a 1 minus alpha times 100% confidence interval for the difference between two population proportions when we have independent samples. The trouble with the approach that we used there is that we have no control over the margin of error. So we could calculate the margin of error and it could end up being an outstandingly big margin of error. So a better approach is to go in reverse. Figure out what is an acceptable margin of error and then use that to determine what the sample size would need to be in order to be within that margin of error that's desired. This is very similar to what we did when we were dealing with a single proportion instead of two proportions. So here we have a couple of formulas that will help us determine the sample size when we're estimating P1 minus P2. That's one population proportion minus another population's proportion. So the sample size required to obtain a 1 minus alpha times 100% confidence interval with a margin of error E is given by N equals N1 equals N2. So what this means is that we're going to assume that the two sample sizes are going to be the same thing, and we're going to just call that N. So we wouldn't have one sample size, say, being 100 and another one being 120. They're both going to be the same size. So N, which is that common sample size, is going to be P hat 1 times 1 minus P hat 1 plus P hat 2 times 1 minus P hat 2 in that quantity, all times Z sub alpha over 2 divided by E quantity squared. Now this will be rounded up to the next integer, and we use this if we have prior estimates for P1 and P2. So those prior estimates are the P hat 1 and the P hat 2. So if we have preliminary information or a previous study that we can use as estimates for P1 and P2, that's when we'll use this formula. Now you might wonder, where does this formula come from? Well, this comes from the margin of error formula that we used in the previous video. If we just take that margin of error formula and solve for N, so again, we're going to assume that N1 and N2 are the same value N. So if we substitute N in place of N1 and N2 in that formula and solve for N, then that would give us this formula. Now, what if we do not have a prior estimate for P1 and P2? Well, if those prior estimates are unavailable, then we're going to use this formula. N equals N1 equals N2. Again, we're assuming N1 and N2 will have the same sample size when we're finished. That's what we're establishing. So we're going to call that N. And so that would equal 0.5 times Z sub alpha over 2 divided by E quantity squared. So notice this part that's being squared is the same here in both of these formulas. The difference here is when we don't have a preliminary estimate for P1 and P2, we're going to use 0.5 instead of this P hat 1 times 1 minus P hat 1 plus P hat 2 times 1 minus P hat 2. Now, why 0.5? Well, if we don't have a preliminary estimate, then we're going to use 0.5 here, 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 and here. And if I substitute 0.5 here, then I would have 0.5 times 1 minus 0.5, and that would be 0.25. 0.5 times 1 minus 0.5, which would also be 0.25. And 0.25 plus 0.25 gives us 0.5. So that's where that's coming from, and that's the maximum value that P hat 1 times 1 minus P hat 1 plus P hat 2 times 1 minus P hat 2 could possibly be. Again, that's very much like when we used 0.25 in this position when we were dealing with a single proportion. And again, we're going to round up to the next integer. The margin of error should always be expressed as a decimal. So this margin of error may be stated as a percent, but we're going to enter it as a decimal in this formula. So let's take a look at an example. Determining sample size. An educator wants to determine the difference between the proportion of males and females who have completed 4 or more years of college. What sample size should be obtained if she wishes the estimate to be within 2 percentage points with 90% confidence, assuming that A, She uses the 1999 estimate of 27.5% male and 23.1% female from the U.S. Census Bureau. Or B, she does not use any prior estimates. So first of all, we're constructing a 90% confidence interval for both parts here. In part A, we have a prior estimate for p hat 1 and p hat 2. In part B, we do not have a prior estimate. But if we're going to do a 90% confidence interval, then this area here in the middle is going to be 0.90. So that means the area in the two tails is 0.10, half of which is in each tail. So half of 0.10 is 0.05, so we're going to have 0.05 in each tail. So I need to figure out the critical value that I'm going to use in my formula. Well, how can I figure out that critical value? Well, we can either use the standard normal table, inverse norm on our calculators, or we can use StatCrunch and use the normal calculator there in StatCrunch. So if I bring in my calculator, I'm going to use the inverse norm command. So the area in the left tail is 0.05. I have that entered here. And so the left value is going to be negative 1.645. This value is negative 1.645, which means this value is positive 1.645 by symmetry. And so that is our critical value in our formula. So for part A, N is going to equal p hat 1 times 1 minus p hat 1 plus p hat 2 times 1 minus p hat 2 times z sub alpha over 2 divided by e squared. Again, our e is 2 percentage points. And so we're going to use 0.02 in our formula. And we know our critical value is 1.645. That's going to go here. And we know that p hat 1 is 27.5%, so 0.275. P hat 2 is 23.1%, so 0.231. And I need a bracket right there. So this is going to equal bracket p hat 1 as a decimal, so 0.275 times 1 minus 0.275, close the parenthesis, plus p hat 2, 0.231 times 1 minus 0.231, close the parenthesis, close the bracket, times my critical value, 1.645, divided by my margin of error, 0.02, and that gets squared. So this is going to give me the sample size. So if I bring in my calculator to type that in, so I'm going to need a parenthesis, 0.275 times parenthesis 1 minus 0.275, close that parenthesis, plus 0.231 parenthesis 1 minus 0.231, close the parenthesis, close the bracket. We have to close the parenthesis, but that's like the bracket. And then that is times parenthesis 1.645 divided by 0.02, close parenthesis, and that gets squared. So that gives us 2,550.523273. And so if we increase that to the next integer, that is going to be 2,551. So we need a sample size of 2,551, meaning that we would need 2,551 males in our study, and we would need another 2,551 females in the study. Now for part B, we do the same problem, except we don't have a prior estimate. So our formula there is that we replace this part in brackets with 0.5. So 0.5 times z sub alpha over 2 divided by e squared. So 0.5 times z sub alpha over 2 is 1.645. divided by E, which is 0.02, and that gets squared. So bringing in my calculator, 0.5 times parenthesis 1.645 divided by 0.02, close parenthesis, squared. And so that is 3,382.53125. So if we increase that to the next integer, that is 3383. So we're going to need a sample size of 3383. So we will need 3,383 males, and we will need 3,383 females. Now there is no command in the TI calculators that will allow us to determine a sample size. But there is a command in StatCrunch that we can use for determining the sample size. This is very similar to what we used when we were dealing with a single proportion. So in StatCrunch, we're going to go to Stat and Proportion Stats. And in this case, we have two samples. And we are looking for the sample size. So I'm going to use the last option, width/sample size. So I get this window. So I have to fill in these parameters, and I need to fill in the width of the confidence interval, and that will give me the sample size. Just like what we did when we had a single proportion, except this time we have two proportions. So our level of confidence is 90%, so I'm going to change that to 0.90. Our first proportion was 27.5%, so 0.275. Our second proportion, which was for females, was 23.1%, so 0.231. And now remember, for the width of the confidence interval, that means the difference between the lower limit and the upper limit. So that's going to be 2 times the margin of error. Well, our margin of error is 2%, so that means the width will be 4%. And we're going to enter that in decimal form. So we're going to have a width of 0.04. When I say compute, StatCrunch will give me the sample size required, which is 2,551, and that agrees with what we calculated by hand. Now this was if we had the preliminary information, or the preliminary estimates for p-hat1 and p-hat2. But what if we don't have a prior estimate? Well, if we don't have a prior estimate, then for the first proportion we use 0.5, and for the second proportion we also use 0.5. So in other words, we're assuming that half of the individuals have the characteristic for both proportions. Again, our width is 0.04, and so if I say compute, I get 3,382. Now when we did this by hand, we got 3,383, so we have a discrepancy of 1, but that is not really very significant. So StatCrunch tells us we would need a sample size of 3,382 if we want to be within a margin of error of 0.02. So again, that would be 3,382 males and another 3,382 females. So this is how we can use StatCrunch to determine the required sample size.